Energized electrical testing. In my career, I've spent a lot of time doing a lot of different applications and about 30 years of experience in thermal imaging. But for the last 20 years, most of that has been electrical testing. And uh, even though the infrared camera is a powerful tool, I found that it is sometimes not enough. However, I wanted to start with a little bit of an analogy. And it's an analogy I use in teaching infrared courses and speaking about the subject. Let's say that you have a medical doctor that's at a conference and they're speaking to non-medical attendees. Out of those attendees, the medical doctor says, I'm going to show you 25 x-rays. And out of all of these x-rays, I want you to mark down which x-rays look like they have a health issue. And they're x-rays of people. So after the doctor shows the 25 x-rays, the entire crowd all points to one x-ray, x-ray number 17, where they can clearly see a broken arm bone. And that's what they announce to the doctor at the end. They say, yep, x-ray 17, the other 24 x-rays are absolutely fine. Then the medical doctor says, well, that is why you need experience, you need to be qualified to actually look at x-rays. You have to be qualified as a radiologist to be able to understand what you're looking for and what you're looking at, because all 25 x-rays showed a health issue. Everybody can see the broken bone, but it's the other ones that you need the training, the experience, and the understanding to look at and determine whether or not it is an anomaly or operating as it should. Well, infrared thermography is very much the same thing, especially with electrical. Everybody can look at the 200-degree hotspot and say, yep, there's a problem. And most infrared cameras, regardless of sensitivity or instantaneous field of view, their optical qualities, even the lower priced infrared cameras that normally wouldn't be able to do an accurate job on electrical thermography can still find that really, really hot electrical termination. So I wanted to share with you a couple other technologies and ways to look at electrical testing. Instead of just calling it an infrared scan, I like to call it energized electrical testing, and there's a lot to it. So with that being said, let's just step aside for a moment and remind the folks watching this what qualification actually means. Qualification is not just attending a very good infrared class or level 1, level 2 class. Those are very important, but it's not enough to be considered qualified for that particular task. To become qualified in a task, according to ASNT's recommended practice, SNT TC1A, you have to demonstrate that you have the skill and have the experience as well, the documented training and the required knowledge, which can come from that excellent course that you choose. Those two are part of qualification, but the experience and the skill has to be there as well. And I'm not going to go further into actually how to get certified or qualified in infrared. It's another subject. But let's just go back to the basics of electrical testing. So we need the personnel that are going to go out there and do electrical thermography or energized electrical testing. They need to be qualified to do so. And when they're qualified, here's what they're looking for. They're basically looking for abnormal heat. And it turns out that electrical energy, which is our power, our wattage, part of that is reactive power. And that reactive power can come from a couple of different parts of the electrical energy. So we have the current and we have the resistance of the conductors. So the current and the resistance are part of what causes some of the electrical power, instead of being used for what we want it to be used for, to become reactive power and heat. So the current, if you see that equation on the screen here, is squared. So the relationship for power to current and resistance, the current squared. That means if you get some current, you're going to get some heating because everything's going to have a resistance. But increasing the current dramatically increases the heating. So we should expect well-loaded equipment to have some sort of heating. And you know, the more load, a lot more heating. Well, how much is too much, and what are we looking for? In my experience, I've never been about temperature. I've always been about looking for the thermal patterns, and some thermal patterns mean different things than others. So one of the things that I want to address real quick is what are the different things that I found that can create heating in electrical circuits? Normal loading, abnormal loading, you know, very, very high loading, sometimes over 100% of the system's rating, higher than normal resistances at terminations or connections. Some components naturally create heat as part of their process. Transformers, RCDs, also known as ground fault interrupters for North America, you know, contactors, overloads, resistors, you name it. Sometimes you have reflected heat. Now that may cause a pattern that somebody may assume that is an issue without understanding that there could be false positives. Total harmonic distortion of the current. So we can have high harmonics that could cause both heating on line conductors and also neutrals if there are neutrals in the system. And environmental issues, so solar loading, nearby components, whatever it might be. The basic electrical scan that most of us do is looking for some sort of thermal pattern. In this case, I've got three poles on this transformer. One of the poles is actually warmer than the other and not consistently, so it could be an issue. As I start to look further into this, I have temperatures and a temperature rise. So we can use all of this information to try to figure out, okay, do we have a problem? And if it is, how serious is it? A lot of people doing electrical thermography will rely on some sort of severity criteria. The severity criteria that I've typically used is from the International Electric Testing Association, also known as NETA. They have an MTS, a maintenance testing specifications standard out there, and they have a table for thermographic surveys to give you suggested actions based on temperature rise, both for similar components and also compared to ambient air conditions if you don't have a similar component. I traditionally use these. They're very good. They're not perfect, but they give us a little bit of understanding of what the severity classification of an item could be. They can't be used for every electrical component, but in general, they work pretty well. So let's give you an example that I took probably 20 years ago. I'll give you the visual of what this looks like, but they're armored conductors at a military base. And I see on these armored conductors, I see a temperature difference between the phases. We have about an 11 or 12 degrees Celsius rise as it stands. Well, it turned out that I had to have a lot more information here to understand severity. So we can't just put this into the NETA criteria and say, yep, probable deficiency, go for it. I needed to know a lot more information. What was the surface emissivity? The reflectance intensity, also known as reflected apparent temperature. Load, we'll talk about that in just a second. Voltage drop, where's the heat being generated at? There's a lot of questions I had to ask myself. One of the things that I wanted to point out here is on this visual, inside the gray box at the top of the image is the disconnect, where the problem turned out to be. The armored conductors had a aluminum or aluminium, as a lot of our folks listening would say, surface that turned out to have an emissivity of about 46 or 47%. So my original temperature difference or temperature rise of 11 or 12 degrees was incorrect. Adjusting for emissivity and reflected apparent temperature, I ended up with a 31 degree differential between the two. But I also had a very, very large armored piece of polymer in between the conductor and where I was looking at on the surface. So the heat was dramatically indirect. This was one of the most critical issues I'd ever found in my entire career. And to top it all off, this disconnect fed a building that wasn't even occupied yet, and this was taking in the winter. So the loading in the building was extraordinarily low. To find this issue at its infancy, or to find it before the building was even occupied, really saved the customer quite a bit, a lot of headache. What additional measurements did I have to take? Well, one of the things, if you're using the ISO standards, like 18434 for your infrared reporting and all that, it definitely says that for quantitative inspections, which electrical typically is, whenever possible, the maximum load of the equipment and the measured load at the time of the inspection. For those of you in North America, NFPA 70B would be the standard that you would use, or it'd be CSA Z463. The measured load and the rated load is still something that we need to report on. So let me give you another example in where this is going and why temperature alone is never enough to really truly understand the health of the equipment in electrical thermography. So this is a disconnect that I took, it's been 2 years ago in Denver. As you can see, I actually used a very high resolution infrared camera with a very, very good sensitivity. It looks a little grainy because there's almost no load on this. This is a 400 amp disconnect with very, very low load, which I'll show you. So I just see that pattern, just a slight little pattern on the line side of the right phase. And I got a temperature rise of 1.7 degrees. Now, according to NETA, that's not a problem. Well, what would I have missed had I not done my due diligence and taken and measured the load and done some of these other things that I highly recommend that you look into? First off, 400 amp disconnect, rated for 400 amps, only carrying 21 amps per phase. It's balanced. That heat shouldn't be there. That tells me there's a resistance there, and an abnormal resistance. So with that loading, we're looking at only a 5% load. 5%, not very much. So what could I do at this point? Well, a long time ago, I was one of the first instructors for a company called the ITC in America. And myself, Dr. Bob Matting, Bernie Lyon, we all put together some research, and we created a load increase or a load change on the amount of heating that would happen in a circuit. Remember, it's current squared times resistance. So all the calculations are here, and this is all going to be recorded, so you can actually go back and look at this and pause it, or I'll assist anybody that would like to reach out to me on this. But a general rule of thumb that we came up with is doubling the load would triple the temperature rise or temperature difference between the components. So if I did that with that example that I just shared, then my temperature rise could be as high as over 130 degrees Celsius. That's the rise between the abnormal component and the other two phases. Well, folks, that is a very serious issue. And had I not measured load and found out that there was only 21 amps being carried on that disconnect, and by the way, that disconnect went to the heating and air conditioning equipment at this building that I was at, a commercial building, and it just so happened to be a beautiful day, and they didn't need heat and they didn't need air conditioning. This was a very critical issue that would have been missed if you just take the thermal imager and go out there and look and say, oh, look, I got a temperature rise of 1.7 degrees, no big deal. That's not how we need to do this. We need to approach this as energized electrical testing. And then that was a fused disconnect. So the next step is, and I'll show you here in a second, the next step is to physically locate the issue with doing a voltage drop. And I'll share that information with you as well. But Dr. Matting and the team came up with a series of calculations. We also figured out that the I squared resistance times resistance, some of the larger, better heat conductive components with a lot of surface area, the current wouldn't necessarily be squared in the equation. So we came up with three different heat conductive property equations. If it was a large bus bar, we'd have the exponent of the current be 1.6. If it was a medium, so a smaller bus bar, 1.8, and then if it was a small conductor, maybe like a single pole breaker with a small, little conductor on it, maybe it'd be a full 2. I think on that larger disconnect, that 400 amp disconnect, I would have used a 1.8 in my calculations, and we created Excel forms that would do this for us. Well, the next step is in that disconnect, heat conducts through metal very, very well. So is the problem at that termination on the line side? Is it at the fuse clip? Is it the bus connection for the fuse clip? Where is that problem? Is it in the disconnect itself in the blade? On that phase that has that issue, and it's more close to the top of that disconnect on the line side than it was on the load side. But what do we fix? Well, folks, voltage will drop or lower with a higher resistance. So if you have a good multimeter that can measure down to the 1,000th of a volt, you can actually use the looking at the current and the voltage drop between the different components by elimination. You can find out exactly where the high resistance is with voltage drop. Or one of the things that I've been doing for a long time is measuring something you can't see with the thermal imager, like an internal moving contact of a breaker. Going across the outside of the breaker, the voltage drop will see what the resistance is inside. So where you have a very indirect measurement with the thermal imager, the voltage drop can actually classify the severity of an issue inside of a breaker. So the voltage is going to reduce as the resistance goes up. Pretty simple, pretty normal electrical measurement. Then also you need to know the current at the exact same time as you're doing the voltage drop, because as you remember, as the current goes up, the heating goes up exponentially, and so does the resistance of copper and aluminum. So we need to know also what the current's doing to our system. So measuring the current simultaneously with the voltage drop. We always use the 2-channel meter that can measure current and voltage drop at the same time. Or if you have two meters, one CT and one. I should probably tell you all. You shall be a qualified electrical person to do this. And most likely, if you're going to go out and do electrical testing, you'll have a qualified person that's out there to take the covers off. If that person's also qualified to use a digital multimeter and knows what they're doing, that individual can also help you with that. In the past, I've always used qualified electrical persons, journeyman electricians, to go out and actually do the thermography as well. And we did that from Australia all the way through North America, all the way through the UK and parts of Europe. So anytime I have infrared thermography of electrical components, I've always worked with qualified electrical persons that also were able to assist me with thermography. So it's a fantastic tool to use. Voltage and voltage drop along with the current. So let's do the actual math behind that last scenario. So when looking at it at its loading, which was only 5% at the time, what would happen? What would happen if the system all of a sudden, was at 80% load or 100% load? Well, the voltage drop, initially on this disconnect was 116 millivolts. That's very high. That's a lot higher. I expected it to be 1 or 2. But to get our voltage drop of on that phase, the hot phase was 98 millivolts versus 7 millivolts on the other two phases. So obviously a higher than normal resistance. What would that voltage drop calculate out to be at 100% load or 400 amps? Well, it looks right here. I don't know if my pointer is working here, but it would be 1.7 volts. That is terrible. That'd be one of the if it actually reached 400 amps or even 300 and some amps, that would be well over 1 volt loss on that phase. That is one of the highest I've ever seen. So very, very, very big problem. Would have been missed if you were doing this with temperature only. And I know I'm very close. I had a couple minutes left, but it's a large topic. I try to cover what I could in about 20 minutes to give you guys some understanding that there's more to just electrical thermography than just infrared and temperatures. Thank you very much for your attention.